Okay, so last time, yes, last week. So what did we do last week? So we finished by we provided the spherical triangular prism equation. So we show that in the spherical case, our previous triangular prism equation, whose picture was quite complicated, can be simplified using can be simplified as follows. But as I already said, this is not the final simplification. We will be able to simplify again. And in fact, today, at least the big part of today will be dedicated to explain how to simplify again and again this picture by adding some assumption. So we will be able to add assumption related to the Frobenius indicator. If the Frobenius indicator, the second one is trivial or the third one is trivial, then we will be able to remove the orientation or to remove the corner. If it is multiplicity 1, then we don't need to specify the morphism. You can replace it by just a bullet. And if it is both multiplicity 1, the second and third Frobenius indicator equal 1, then you don't need to put orientation. You don't even need to write the morphism. You don't need to write a bullet. You don't need to put it as a corner because the third Frobenius indicator is trivial. You just need to label the edge. So you only need to keep this kind of label. You can remove that, remove the orientation. You can remove that. You only keep that, etc. So we will explain briefly these steps. Okay, so last week I finished by drawing the three representation of the triangular prism graph. So remember that we use this one as a model for the monoidal triangular prism. We use this one to explain the idea of the triangular prism equation, to explain the proof using the Dylan-Thurston picture. And now we will use this one to simplify. We will use this one as a simplified triangular prism using the symmetry and the sphericality. Okay. Okay, so the first is the one we used in definition 6.1, so the monoidal triangular prism. The second is the usual one. By usual, I mean in graph theory, this is the usual way to depict this graph. The more regular, the more symmetric one, which was mentioned in introduction with Dylan-Thurston picture, providing the idea of the proof of the TPE. And the last one so the last is the one we will use now. Okay. So in the coming next See the coming definition 8.8. Okay. Let me check. So let me recall again about the symmetry of the triangular prism. The following, we mentioned a remark about that. We can realize the orientation preserving symmetry group, the symmetry group of order 6 of the uniform triangular prism. As we did for the regular tetrahedron. The following, we can realize the orientation preserving. So we already mentioned that. Orientation preserving symmetry group six of the uniform triangular prism. So in 3 dimensions. As we did for the regular tetrahedron. So that's okay. In remark 8.4. Okay. Okay. So we provided a simplified version for the tetrahedron. Now we will provide a simplified version for the triangular prism. So the monoidal triangular prism in definition 6.1 can be noted. So as we did for the tetrahedron, as for definition 8.1, using the following definition, using the following reference pattern, if you like, the following definition. So, which will exactly use this representation of the triangular prism graph. Definition 8.8. Okay, so the following definition 6.1. This is for the notation. So we follow the notation of this definition so that we don't have to rewrite it again because it's quite long. We define it as follow. Okay, so we have something here, here. Okay, so this is the triangular prism graph. Now we will put the label and orientation. So in the middle, everything go to the left. On the right, you are going like that. On the left, you are going like that. This is for the orientation. Now you have x1, x2, x3 in the middle. And the left, you have 4, 5, 6. 4, 5, 6. On the right, 7, 8, 9. So you see it's more regular now. More intuitive, maybe. And let me change the color for the morphism. So morphism, alpha 1, alpha 2, alpha 3 on the left. and alpha 4, alpha 5, alpha 6 on the right. Do you see? That's nice. So this is the reference pattern for what was the monoidal triangular prism. Alpha 3, alpha 4, alpha 5, alpha 6. So I will not come back to the monoidal triangular prism because it was far. But remember, it was something. Remember, it was something like that. You have something like that, and then you have something like that, something like that, something like that, etc., something like that, etc. So if you attended the course, you exactly remember what I mean because this was one of the biggest picture of the course. So now we can only consider this picture. This will be our reference pattern. Of course, we still need to apply, we still need to consider our rules 1, 2, 3. Remember that. If you want to move some labeling of morphism. Okay. So that's okay. That's nice. Do you see? We started from this graph. So you have this graph, or this graph, if you like, the regular. And you have this graph. And so using these two graphs, we can write an equation by evaluating this one by such graph with label. So this is the idea of the proof of the triangular prism equation. So let me write a remark first before going further about this notation and before mentioning the additional simplification. I want to put a remark about the fact that it is possible to get equation if you start from another graph. Here, the triangular prism and the tetrahedron graph are the two planar graphs with less than or equal to 6, with at most 6 vertices. But there exists planar trivalent graph with, for example, 8 vertices. So it's easy to see that a planar trivalent graph should, a trivalent graph should have an even number of vertices. So so for 6 and less than 6, it's known. You have 2, you have this one and this one. Now for 8, we have 2. There is also 2 planar trivalent graphs. One of them is the cubical graph. So I will draw it, and as an exercise, you can try to provide the monoidal cubical the monoidal cube, and to get the equation from that. It's a good exercise, and in fact, you can do that for any planar trivalent graph. It will be. So I will mention something else in the remark about what could we potentially do about this extra equation. Of course, as we said before, the triangular prism equation are equivalent to the Pentagon equation up to a change of basis, but they are equivalent. So this extra equation with planar trivalent graph with more vertices uh, will, how to say, will be, will not provide essentially new equation because in fact, the constraint by this extra equation is already contained in the constraint of the Pentagon equation or the triangular prism equation. But the idea here is that these equations are huge. And so it's always good to find other way to find new perspective, new insight. And so this insight of using graph with more than 6 vertices was not developed in this course, in this paper, but it's a good idea to develop. So that's why there is this remark. So in general, we expect to get equation as the triangular prism equation, we explain, from every planar trivalent graph. Every planar trivalent graph. And in fact, at the end of the section, we will generalize this remark to any trivalent graph. But then we need to consider braiding, because if it is not planar, then you have some crossing, and the crossing should be handled by braiding. And so, in general, we expect to get the equation for every trivalent graph. And if it is not planar, you have to use braiding. So here, now we are only for planar. So for every planar trivalent graph, inheriting, so with the symmetry, inheriting the symmetry of its regular geometric realization. So you have a planar trivalent graph, and for example, the tetrahedron, the triangular prism, or the cube, there may exist a regular geometric realization with a lot of symmetry. And in fact, we expect that all this symmetry pass in the monoidal or spherical case framework. So inheriting the symmetries of its regular geometric realization. Realization when it exists. Maybe you can have a trivalent graph, planar trivalent graph, without symmetry, without I don't know, without geometric realization with symmetry. I don't know. But you can also have graph with so many symmetry that it's interesting to develop or to explore this way. Example. So, as we already mentioned, the only planar trivalent graph with at most 6 vertices are the tetrahedron and triangular prism. The only planar trivalent graph with at most 6 vertices are the tetrahedron and the triangular prism. And the triangular prism graph. With less than or equal to 8 vertices. So remember that the number of vertices should be even. So less than or equal to vertices. So wait. Then there are two more graphs. There are two more graphs, one of which is a cubical graph. One of which is the cubical graph. So the graph of the cube. So like that, as you can expect. So it has a planar representation, but its regular representation is in 3 dimensions, the cube. But you have this representation. So this is very similar to this one. And in fact, you easily see that you can extend that to, here you have 3 and 3 inside. Here you have 4 outside and 4 inside. You can generalize something like that. You can generalize, and you can have as many graphs as you want, like that. But here the symmetry group is much bigger. So the symmetry group here of the regular cube is S4. So the symmetry group S4. I guess orientation preserved. Okay. So that's interesting. So as an exercise, you can try to make the monoidal cube as we did the monoidal triangular prism, and to evaluate it with monoidal tetrahedron to get new equation. As an exercise, you can write the monoidal cube. So maybe as for the triangular prism, maybe this will not be the more appropriate model. Maybe you will need to use another model which is equivalent to this one and evaluate it. Evaluate it by several ways. There may be more than 2 ways. For the triangular prism, we have 2 ways, but here you may have more than 2 ways using monoidal tetrahedron. To get some new equation. So as I said, the constraint of this equation are contained in the constraint of the full system, or to be more mathematical, you can say that you have you can say the Pentagon equation or the triangular prism, the system of Pentagon equation or triangular prism equation, as a system of polynomial equation with several variables. So all these variables generate a ring, something like so the coefficient of this equation are, let's say, a ring like that with multiple variables. And the Pentagon equation generates an ideal. And in fact, on the triangle generate an ideal. So the equation for should be in the ideal of the system of Pentagon equation. So there is nothing essentially new, but that can provide new insight, new local system, something can be interesting. Okay, so to get some new equation, say cubical equation. Cubical equation. In fact, I already saw some papers where they are using such cubical equation. Okay. So it will be nice. So this is the extra part of the remark I wanted to say that. So it will be nice to find a fusion ring which is open to categorification, but which can be excluded using an appropriate planar trivalent graph, which is not the tetrahedron, which is not the triangular prism. So we did that, in fact. So we will explain some application in this course of the triangular prism equation. We will be able to exclude a fusion ring from categorification using this framework, a fusion ring which cannot be excluded otherwise by any other criterion or any other techniques. This is the main application for this system because this fusion ring was the last to get a theorem, classification theorem for the unitary simple integral fusion category up to, I don't remember, rank 8 and Frobenius per dimension less than 5,000, something like that. So this was the last example, so the hardest one for this classification. And so we use our framework to rule it out. But you can imagine other fusion rings, even harder to exclude. And we need to find an appropriate graph, an appropriate geometric object to exclude them. That will be nice. So it would be nice to exclude, or even or to categorify if you a fusion ring. I say to categorify like that, but usually to categorify you need more than you need to consider all the system. But yeah, anyway. So a fusion ring open to categorification. Open to categorification using the equation of an appropriate planar trivalent graph. Appropriate planar trivalent graph. Different from the TP. So we did that. We already used TP to exclude a very hard one. By one, I mean a fusion ring. The last one to classify the unitary simple integral fusion category of rank less than or equal to 8 and Frobenius per dimension less than or equal to 5,000, or about 5,000, I don't remember the exact. So this is very useful. Okay. So this will be a theorem, in fact, in the course. Theorem all the unitary simple integral fusion category like that are of the form rep PSL to Q. Okay, so that's all for this remark. Now, let me add I have to, okay, wait, careful about something, come back to 71. Okay. Okay, so now okay, we will talk about another way to simplify by considering what in a paper of Haag and Hong called strictified skeletal. So we will be able to assume that the double dual is the identity and for the object, and the fourth dual is the identity for the morphism. So for categorification problem, we only need to consider this case. So according to a paper by Haag and Hong, paper in 2009. So this paper is mentioned in my paper as the reference 10. So according to them, any fusion category C is equivalent to one called strictified skeletal. The equivalent is equivalent to one strictified skeletal. So I guess, so remember that in some previous semester, we mentioned that every monoidal category is monoidally equivalent to a strict one. I guess this was MacLean strictness theorem. Is also monoidally equivalent to a skeletal one, but they cannot be both monoidal equivalent to a strict and skeletal one. But you can apply you can make it skeletal or make it strictified. There is a process for that. And if you first make it skeletal and then strictified, strict, so it's no more skeletal, but it keeps some extra property. It's called the strictified skeletal. I hope it is in this way. First skeletalification and then strictification. Maybe it's first strict and then skeletal, I don't remember, but according to the name, it should be strictified skeletal. Anyway, doesn't matter, we can go to this reference. We only need is the property. So in this case, the double dual is the identity on the object. And the fourth dual is the identity on the morphism. On the morphism. Okay. But when we are talking about categorification, we only need to care about up to equivalence. So if you can assume that up to equivalence, it's enough. Well, we can assume that for categorification problem. So about categorification problem. We only need to consider this case. This case, which simplifies the way to write the triangular prism equation. Which simplify the way to write triangular prism equation. Okay. But we can simplify even more. Yeah, so this is really conceptual simplification. Now I will explain a non-conceptual, purely technical simplification. In fact, because we are now in the spherical case, we can, in fact, we can modify a little bit the notation for the morphism. So we will provide a new reference pattern, which has extra symmetry, which is more regular in some sense. So you have to be careful. It will be a little, there will be a small variation with this one. But in fact, this one is a pattern corresponding to that. And when we are in the purely monoidal case, this extra regularity cannot be applied here. But in this spherical framework, we can do. Okay. TP, to simplify even more, we improved a bit the definition of some morphism. Alpha I and beta I in theorem 810. So theorem 810. What is theorem 8? The coming theorem 810. Coming. So in the coming theorem 810. So be careful. That differ a bit from theorem 8.6. Theorem 8.6. Okay. So such simplification will not be possible before. Such simplification will not be possible. Will not be possible from the beginning, because it requires extra assumption. The extra assumption we use now. So from the beginning. So beginning here means theorem 6.3. Okay. So the variation on the morphism. So the variation on the morphism alpha I permit to get the following oriented label triangular prism So I will draw a new version. The variation on the morphism alpha I permit to get the following oriented labeled triangular prism graph. Differing on the orientation. So, sorry for this very technical aspect. It's not very important. Of xi for I equal 1, 2, 3, 7, 8, 9. Okay. So be careful. So now we have the new pattern. So it's quite close, but this new pattern will be more convenient for the rest. Okay, so everything, so the orientation is like that here, and then like that, and like that. So differing on the orientation of, okay, 1, 2, 3, 7. So the orientation of, so this one and this one was not the same. So here is going like that. Here is going like that. Like that, like that. Before, it was like that and like that. So like that, like that. I don't know. This differ only on 1, 2, 3, 7. Only this one differ. This one are unchanged. So the modification, so this one are the same. Here you have like that, and here you are like that. Okay. So otherwise it is the same. So x1, x2, x3, x4, x5, x6, x7, x8, x9. So you see, you have an extra symmetry for the. This is more symmetric. This is like that and like that. Okay. And the morphism, the same. So 1, 2, 3, 4, 5, 6. Okay, so this we will refer to this pattern, this picture, as a figure 1. So we will mention it later. So we can make the pause now. 5-minute pause. Okay. So that will be the reference pattern from now. We come back to 71. Okay. So, theorem. So because we redefine a bit we put more appropriate morphism, I have to rewrite the list of notation. theorem 8, 10 called simplified TP. Okay. So in fact, in the statement of this theorem, we will assume even more than what was provided by Hag Hong. So we will use that. That's okay. So x double star equal x. But we will also need that the square of the pivotal structure is the identity. And that I don't know if we can, for the application, so I mean, we want that also. So I don't know if we can deduce that from that. Is it true that every fusion category is equivalent to a fusion category where you have that and where the square of the pivotal structure is the identity? We will need this assumption to simplify even more, and for the application of that, the application will follow this assumption. There is no problem. The question here is, can we write a more general statement? So at the time I wrote this part, I was only focused on the application, so I did not take much time to try to generalize, but anyway, so let C be a spherical fusion category such that x double star equal x and the square of the pivotal structure is the identity for any object x in C. So yeah. So where a square is where A is the square is the pivotal structure. A is the pivotal structure. So in fact, as we will mention later, this assumption is automatically satisfied if every simple object is self-dual. Because if every simple object is self-dual, if you have that, then you can apply some previous theorem involving the second Frobisher indicator, which is plus or minus 1. So the square of that is 1. So this is identity. And this is a case we will apply. In fact, this is a little bit more general than just saying that let's see be a spherical fusion category where all the objects are self-dual. You can at least have this more general statement, but the question is every spherical fusion category equivalent to a category with that? Otherwise, we will need extra work to generalize our result. But as I said, the result was applied in a case where it is true, so it's okay. For any object, okay. So let, now the notation, let xi I equal 1 up to 9 be object in C. Consider the following morphism. Consider morphism alpha I in So now I use a simplified way to write this notation. The home space of morphism in 1 and yi, I equal 1 to 6 with, so we just need to describe every yi, y1 equal x4 tensor x1 tensor x6 star, y2 equal x5 tensor x2 tensor x4 star, y3 equal x6 tensor x3 tensor x5 star, y4, y5, y6, and that will be complete. So x1, x9 star tensor x1 star tensor x7, y5 is x7 star tensor x2 star tensor x8, and y6 is x8 star tensor x3 star tensor x9. Okay. Then the following all, and we will see no more so the big advantage here is that there is no more natural transformation rho and sigma. The following TPE hold. In the previous version, we still have this natural transformation. Remember, the previous version was here, and we still have to consider this kind of, now we will no more need, no more, according to this, using the assumption. And, okay. So, okay. So, sum. So it's simplified, but the structure, the global structure will be the same. So you will have two so yeah, almost the same. So two will be equal to something with 3. So this is the same global structure. We have 3 now. One, two. It's too big. Always the same problem. Okay. So okay. So sum of product of 2 tetrahedron equal a sum of product of 3 tetrahedron. But now you can you no more have the natural transformation rho and sigma. So now beta 0 are inside beta 3 prime, beta 1 prime, beta 2 prime, beta 1, beta 2, beta 3. So this is the element of the basis. And the so alpha 1, alpha 2, alpha 2, alpha 3, alpha 4, alpha 5, alpha 6. Here you have alpha 1, alpha 2, no, alpha 4, alpha 2, alpha 5, alpha 3, alpha 6. Okay, now the morphism, the orientation. So everything inside, everything outside, and then you move, you go around like that, and here you go around like that. So you see, here it's like that, here it's like that. And here you have like that, XXX, and then it turns around like tac, tac, tac. The same for everything. So it's a regular, you have a regular pattern for every. So I guess, wait, I made a mistake here. Should be like that. Go up. So everything go up like that, up, 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 down, 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 and right, right, right. And inside, sorry, again, I forgot to write the orientation inside. So let me check. It's like that. Okay, and finally, the labeling of the object. So 1, 2, 3. X1, X2, X3. 1, 2, 3. Then 4, 5, 6. And 7, 8, 9. Okay, now X, X, X. 1, 2, 3. Then 4, 7 here. 4, 7 here. 5, 8 here. 5, 8 here. And finally, you have 6, 9, and 6, 9 inside here. Okay. So this is a current, and I forgot the dimension X. So this is a current simplified version of the Triangular Prism equation, which work with this extra assumption, and this extra assumption work if every simple object are self-dual. And so the question I ask, how to generalize this simplification without assuming, so is it, yeah. Is it always true that we can reduce to this case? I'm not sure. Okay, so dx is the usual dimension, categorical dimension. Okay. Big O is a set of simple sub-objects of both X4 tensor X7, X5 tensor X8, x6 tensor x9 up to isomorphism. Okay, and the basis BI. So I repeat, I have to rewrite the notation because there is a small difference with the previous version. With z0 equal x1 tensor x2 tensor x3, z1 equal x7 star tensor x tensor x4 star, z2 equal x8 star tensor x tensor x5 star, and finally z3 equal x1 star tensor x tensor x6 star. Okay, and beta I prime in bi prime is the dual basis of bi according to, so this is the same as before, according to the binaire form in lemma 3.2. Beta map to beta I prime is the usual bijection. So I repeat that beta I prime is not the dual in the sense of category. This is just a notation for the usual bijection between dual bases. Okay. So now, so that's okay. So we have this nice simplified version. So now we can simplify even more if we assume more about the Frobenius indicator and the multiplicity. So this is what we will explain now. And I guess it will be enough for today. Let me see. So remark 8.11, more simplification. So let's see. Be a spherical fusion category. Spherical fusion category. Let x1 up to x9 be simple object in C. So by proposition 217, the assumption of the previous theorem is always satisfied if the self-dual case. The assumption in theorem 8.10 are always satisfied. Always satisfied if X is self-dual for all simple objects. X in C. Okay. And so we will apply this result. We will apply the theorem in the self-dual case. So it's okay, but if we want to apply the simplified theorem for a non-self-dual case, or if you know that the square of the pivotal structure cannot be identity, it's not equivalent to a fusion category where the square is identity, we cannot apply this simplified version. But we know that this theorem involving the second functional indicator, in this case, it's okay. Now, more. So now we can do more. If moreover, so moreover means that we are in the self-dual case. If moreover, the second from issue indicator is 1 for all simple objects, then you don't need to orientate the edge. So there is a lemma, I don't know, 7.5 lemma involving the orientation and the second from issue indicator. So if it is involving maybe it was about the evaluation map plus or minus, and we say we can go from one to the other by using the from issue indicator. So if it is trivial, then both are the same, and so you don't need to orientate. So if moreover the second from issue indicator is trivial for all simple objects, X, then by lemma 7.5 I just mentioned, there is no need to orientate the edge. So we have something like that. I can draw some picture. I have to check that. It will be more convenient. I don't have time to check now, but anyway. Anyway, so you can simplify as follow. So 1, 1, 2, 3. Okay, so let me move this a little bit. Yeah. Okay, so here you have sum of beta 0 in B0. Here you have sum. Yes, I should have rewrite that. I'm not sure. It's too long. I hesitate. Should I write that or not? Or very quickly. Without color. It's too quick. Okay. So in fact, you don't need orientation. So alpha. So 1. It's very boring. It's too boring. So beta 0 prime, beta 0, beta 3 prime, beta 1 prime, beta 2 prime, beta 3, beta 2, beta 1, alpha 5, alpha 2, so 1, 2, 3, alpha 1, alpha 2, alpha 3, alpha 4, alpha 6, alpha 5. So alpha 1, alpha 4, alpha 2, alpha 5, alpha 3, alpha 6. So x. So this is exactly the same as before, but without orientation. It's useless to write. One, two, three. X6, X9, X5, X7, X8, 4, 7, 5, 8, X6, X9, and I forgot again. Here you have X6, X9, 4, 7, and 5, 8. Okay. So sorry, it was boring. Okay, so alternative. So you can write this. So this is this one without orientation. So it was too quick. This is not beautiful. But... So alternatively, the morphism label of a one-dimensional home space can be replaced by a bullet. So remember, what's the point? What is the point of writing morphism here? Why you need to write a morphism? Because this one, for example, or this one. Because there are the basis, so the set, the space of possible morphism for these three objects is more than one dimensional. So you need to specify which morphism you consider. And in fact, here in the equation, you make the sum over a basis of this home space. In general, the home space is more than one dimensional. So you need to fix a basis, and then you need to make the sum here, and you need to specify which morphism you consider. But if the category, if the fusion category is multiplicity-free, which means that the home space for three objects like that, which are simple, are always at most one-dimensional, which means that you have only one choice of morphism up to multiplicative constant. And so you don't need to specify the morphism. You need to specify the corner because we don't assume the third formulation indicator is trivial. We will mention that later. But at least you only need to specify the corner. So you don't need to write any sum here. This is what we will write now. So alternatively, but I am too stupid. Maybe I can just copy and paste that and remove the... Let me check. Can I copy, paste? Yeah, good. Copy. So sorry for this one, but I will paste. Yeah, good. Oh, no. Yeah, it's okay. So I will. So I was stupid here. I could just do that, but okay. So I still need to write some sentence. No. No, I need more space. Okay, like that. Okay. So I will modify later. Alternatively, the morphism label of a one-dimensional home space can be replaced by a bullet. So if every involved home space is one-dimensional, so if every involved home space is one-dimensional, in particular, the multiplicity-free case, in particular, if the Grothendieck ring ring is of multiplicity 1, which means nijk if less than or equal to 1 for all ijk, then we can simplify as follows. So then we can remove and put a bullet and that's much better to do that. It's much more convenient. And we can remove also this one and this one. And we need the bullet. So we just need, you can have this simplified picture. Same for the, in fact, same for the picture for the triangular prism. You can replace the morphism by bullet like that. Oh, I missed one. Okay. And here, that's better. That's better. Wow, that's much better. Okay. 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 And finally, now we have the technique. We don't need to draw again and again. We can provide an extra simplification. Finally, if we have all the possible simplification, so if it is of multiplicity 1, with x star equal x, we have everything. The second and third from initial indicator is trivial for all simple objects. X, then no orientation and no bullet. No orientation and no morphism, no bullet, not even bullet. And the no bullet is by the lemma 8.2 with the third formulation indicator. So remember, so this corresponds to no bullet and this to no orientation. And so we can maybe I will copy this one. And it will be there. Okay. No, not okay. I will remove this line. Okay. Okay, so we can remove everything. We can remove that. We can remove that. We can remove that. We only keep the object. We only need to keep the object. Oh. Okay. That's okay. We have this. I forgot here. X1, X2, X3. I guess I forgot it from here. So X1, X2, X3. Okay. 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 So, so sorry for the picture, which is not nice here. But you understood the idea, of course. Okay. So now I will finish the section with a remark for non-planar graph. And in fact, you have a non-planar graph with a 6, we have an extra non-planar trivalent graph with 6 vertex. And we will draw something. We will generalize, or we will adapt the monoidal triangular prism for this small variation with this extra crossing involving braiding. So, but I may have no time to explain everything, but let me start. So let us finish a section, some comment involving non-planar trivalent graph and braidings. Let us finish this section by some comment involving non-planar trivalent graph and braidings. So as I said, so there is a third trivalent graph with at most 6 vertices, apart the tetrahedron and triangular prism graph, but it's non-planar. There is a third trivalent graph with at most 6 vertices. So we have an extra one with a third apart so the tetrahedral and triangular prism graph. Tetrahedral and triangular prism graph. But it is non-planar. 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 It is called the complete bipartite graph K33. K33. The complete bipartite graph K33. Here are 3 representations of it. Representation of it, which will look like the representation we used for the triangular prism, at least for 2 of them. So the usual way to draw this graph, so the complete bipartite graph, bipartite means you have 2 parts, and complete means you have to draw everything. So this is like that. Complete bipartite graph. So you draw everything in a bipartite way. But this is equivalent to this graph, in fact, which look like much more something which is close to the regular representation of the triangular prism. You see they will have a small variation. Here is the same, here is the same. The small variation is here. We will have something like that. And to finish for today, the third representation we will use to provide this variation for the triangular prism, braided variation. So you have that. This is the same as before. And like that. So you have something like that. And then this as before. There is no vertex here. It's just to depict where is the variation. It, as before was like that. And here it was like that. So you see the small difference. And we can write the pattern for a small variation, a braided variation of the triangular prism, monoidal triangular prism. We will draw it. And we will leave as an exercise what kind of equation we can get from that. So we stop here. Arrêtez. Arrêtez.